In this lesson, we are diving into the JWT Secured Authorization Request, or JAR for short. This extension to the OAuth 2 flows addresses the security challenge of the initial authorization request that we discussed in the last lesson. JAR is a security-enhancing extension that can be applied to all user-initiated flows that supports confidential clients, meaning it works with both the authorization code flow and the PKCE flow, but only with confidential clients. We'll explore why it is limited to confidential clients shortly. Let's take a look at how JAR works within the PKCE flow. We are still working with the same OAuth 2 roles. As usual, the resource owner initiates the flow by wanting to log in. The client first generates a PKCE proof key for code exchange and stores the code verifier securely. Next, the client creates the authorization request parameters that are typically sent as query parameters in the URL, such as client ID, redirect URI, scope, state, code challenge, and code challenge method. But instead of including these parameters in the URL, the client creates a JWT JSON Web Token and packages them into its payload. And then the client encodes the token, both the header and payload, in base64 URL format. The client then signs the JWT using its private key. The recommended signing algorithm here is asymmetric with RS-256, RSA using SHA-256, which ensures stronger security by utilizing a public and private key pair. This means that the client must securely store its private key for signing the JWT, as the integrity and authenticity of the token rely on this key. To validate the signature, the authorization server must also have access to the client's public key or know how to retrieve it. We have already covered the basics of asymmetric signing in the token validation lesson, and exactly because of the private key that should be securely stored by the client, we need to register the client as a confidential client. Once the JWT is signed, the client then sends the resource owner to the authorization server along with the signed JWT and client ID as query parameters. The authorization server validates the JWT's signature using the client public key and extracts the parameter from the token. From here, the server stores the code challenge and code challenge method, and everything proceeds as usual. The resource owner then authenticates, and the authorization server generates an authorization code and redirects the resource owner back to the client. Let's now see how the JAR flow addresses the security challenge we discussed in the last lesson, using the same scenario with a malicious application. The client begins by performing the 5 steps of the JAR flow. It first generates a PKCE with a code verifier of CVXY and creates the authorization request parameters such as the redirect URI, scope, and code challenge. In this case, the code challenge is equal to XY. Next, the client includes all these parameters in the JWT payload, then encodes and signs the JWT using its private key. After this, the client sends the JWT to the authorization server by redirecting the resource owner via the user agent. Now, suppose the malicious application intercepts this request again and attempts to manipulate the parameters like replacing the code challenge. The attacker generates a new PKCE with a code verifier of CVAB and it changes the code challenges from XY to AB in the token payload, sending the request to the authorization server. And here is where the critical difference lies. The first thing the authorization server does is validate the JWT signature using the client's public key. Since the attacker has modified the payload, the signature no longer matches the original signed authorization request. As a result, the authorization server detects the tampering and rejects the request, which makes the attacker very sad.